Hi, I'm going to present some work that suggests that stellar prominences could be an important but invisible mass loss mechanism for young stars. So this research is from a paper that we published last year, and you can find it on arXiv or MinRes. And I'm going to focus on just one part of the paper since this is a 10-minute talk. And that is that prominences could be removing as much mass as the stellar wind, but that we might not observe them. These plots are of mass loss rates per unit surface area against X-ray flux. And I'll be back later in the talk when I'll give a bit more detail about them. But right now, the main point I hope for you to see is that prominences, the modeled prominences from this work on the left-hand side, show the same behavior as the wind that I've shown on the right-hand side, taken from previous studies. So prominences are condensations of plasma. They're supported above the surface of the star by a magnetic field. And material is supplied by a thermally driven upflow of material from the surface to the loop summit. And this is the same as the thermal wind. When they become unstable, they're ejected from the star, removing mass and angular momentum. And in some stars, we would expect to see limit cycle behavior. So this is when prominences form and eventually become unstable, so they're ejected. But the magnetic field is pretty stable over the long term, so it reestablishes itself and prominences reform, they're ejected. And this cycle just repeats. And this is similar to an intermittent wind, where kind of similar to the wind just switching on and off. We see these slingshot prominences on rapidly rotating stars. So examples of stars that you might have heard of include AB Doradus or Speedy Mick. And they're observed as absorption features in the H alpha line. And so there's an observational plot on screen. And so we see this absorption feature when the prominence transits the stellar disk. So they have to pass in front of the star for us to see them. And they form above the co-rotation radius where the gravitational and centrifugal forces balance. This is why they're always ejected. And they are quite large, 10 to 100 times the mass of solar prominences. So they differ from solar prominences in terms of their mass and their size, but also their distance from the star. Winds of cool stars are difficult to observe due to their low densities. With that said, there are a few methods by which their mass loss rates can be deduced, and the data from these are shown on this plot here. So again, the vertical axis is the wind mass loss rate, and the horizontal axis is the X-ray flux. So a few of the methods include the interaction of the wind with a planetary atmosphere. The method that has produced the most points on this plot is the interaction of the wind with the interstellar medium. They're all the red points. And a third method was shown by Jardine and Collier-Cameron, which involved calculating the mass loss rates of the observed prominences and using these to predict the wind values. So the plot here, whilst it shows a correlation between the X-ray flux and the mass loss, there is quite a lot of scatter. And what I've done is reproduce this plot, but for some modeled prominences. So I did this by calculating the mass loss rates for these prominences, which are theoretical calculations, not on observer. So I started with the observed Zeeman Doppler imaging maps, which give the surface magnetic field, and then the coronal field structure is generated by assuming a potential field. The locations of the prominences are found by finding the mechanical stable points in this field structure. In the image I've shown on screen, that's the purple points. And then the mass loss rates from these prominences can be found by assuming that material is applied to the stable point by a thermal wind. So here are the results for these modeled prominences. Like the observed wind values, they also show a lot of scatter. The blue dashed line shows the line of best fit for this work. And the other lines are the relations given from the wind studies in the literature. And the prominences do fit very nicely with the wind relations. But if instead of plotting all of the prominences in the model, we only plot those that would transit the disk and be visible to observers, then it's a different matter. So the top plot is the plot that I showed on the previous slide, and the bottom plot is the plot, like this plot replotted, but I've only included prominences that would have transited the disk. So only the ones that would be seen by observers. And the point really is that many, if not most, of these prominences in the models just simply aren't visible. They never transit the disk, no matter how long you wait. So firstly, there are likely a lot more prominences around these stars than we know from observations. It probably also means that there are lots of stars out there where we don't observe prominences, these slingshot prominences, but that they are still there. And it also means that if we are going to use prominences to predict mass loss rates of the wind, we should be careful and keep in mind that observations are definitely going to be underestimating the amount of material around these stars. So thank you for listening. Feel free to contact me by email, on social media, if you're into that kind of thing. And you can read the paper as well to find out a bit more about this and some of the other stuff as well that's in the paper. So there's an archive link and also a QR code if you're interested. So yeah, thank you for listening.